Hey, it's Tony from Adafruit, and in this video I wanted to just play around with MicroPython and NeoPixels and see if I can recreate some cool things that are demo scene effects, some old school demo scene effects actually, and I'll look at exactly what that is in a moment here. But really just wanted to do something a little bit fun, play with NeoPixels and some hardware in MicroPython and just build some kind of cool, interesting display, something that might be a wearable even, something that's kind of eye-catching and attention-grabbing. You know, Maker Faire, World Maker Faire is coming up pretty soon, so you have to have some neat MicroPython projects and things for that. So yeah, this is a little bit less scripted than previous things. There's no code that's up or no tutorial that goes along with this yet, but maybe in the future I'll probably put some up here. I figured it'd just be interesting to look at how to recreate some interesting effects and things and just play around with MicroPython and see what's possible with this. So let's just kind of dive in real fast to the main view here. Let's see, let's do that. There we go. And so I've got a couple interesting things here, and maybe before I jump too far into what I wanted to cover in this video, I'll show something neat. This is maybe a don't ask, it's not out yet kind of preview. So this board right here, this is, and it's a little bit hard to see, we'll see if I can hold it a little bit closer. So this board, this is the Feather M0 Proto board. So this is basically an Arduino M0, but just with a little prototype area where my thumb is, so there's nothing else really connected to it. And the Arduino M0, if you remember, is the Atmel SAMD21 microprocessor. That's a Cortex M0, bunch of fancy words. It's basically a more powerful Arduino, has more memory, has more processing power, maybe not as much as like the Due or some of the other fancier Arduinos, or like a Teensy has a more powerful Cortex processor. This thing's a little more low end, but the cool thing is Scott, who's another person at Adafruit, has been working on porting MicroPython to it. So let me plug this thing into my computer right here, and I'll actually show you real fast that this will actually show up as a MicroPython type device. So if I connect to the screen, the serial terminal, so it creates a USB to serial connection here, and it looks like a USB modem device basically. So if I connect to this, then hey, check this out. Adafruit Feather M0, Bluefruit, this is a little bit in development kind of stuff right now. But this is MicroPython running on the Atmel SAMD21. Now it's not a full implementation, like, you know, there's just the basics. We have digital I/O, analog I/O, some of the things like I2C access. So just, you know, it's kind of early days, but really cool and impressive that we've got real MicroPython. So, you know, here, hello world, we can print things out. And again, this is running on little Cortex M0 on this Feather M0 board. And so this processor has, if I remember correctly, 256 kilobytes of flash memory, and I believe 32 kilobytes of RAM. So that's pretty small in the MicroPython world. Like the ESP8266 has, depending on the board, like 4 megabytes sometimes of flash memory. And then RAM, there's around 96 kilobytes or so of flash memory. So this will be kind of interesting. It's, you know, a little bit lower spec device, but these things can be a little more inexpensive, or we have all kinds of different feathers and things to go with this. So look for more fun in the future with this, but I just wanted to show that there's going to be some cool stuff coming with the SAMD21 for that. Okay, so the next thing, this thing right here, this is kind of cool. So this is something that I built just using the Arduino NeoPixel shield. So let me grab another one that I have handy here. So this is, if I lose all the parts for it, come on, pull this out of the bag, there we go. So this thing is the Arduino NeoPixel shield, and when this video goes up on YouTube, I'll put a link to all the products here and things that I mentioned. But this is made for an Arduino, so you're supposed to take, you know, your Arduino, and then you've got your Arduino shield, and you solder the headers onto this thing, obviously, and it goes on top of here. And it gives you a nice grid, an 8x5 grid of NeoPixels. So you can light these up, you can do all kinds of cool animations and things. But I thought, you know, this would be a good base to use as an interesting MicroPython device. So I took one, and I actually soldered, well, first I taped an ESP8266 on here, and then I just soldered some connections to the NeoPixel input, the power, and the ground. This is just a little LiPo battery that I put some gaffer tape on, so it's a little more protected. And there's Velcro here, so you can actually Velcro this battery right to this open spot right here. So the whole thing can be kind of self-contained. And these are actually little clips or pins that you can use to put this on clothing, because this could be kind of a cool wearable, like a name tag or something. You know, you pin this to the front of your jacket and maybe scroll like a message across the pixel grid, overhead or something cool, you know, just maybe animate some neat effects like I wanted to play with here. But it's an ESP8266 that's powering this. This thing has obviously MicroPython firmware loaded on it, and this is a grid of NeoPixels. Now these shields that I have right here, these are the RGBW NeoPixels, and these are the soft white color, I believe. So it's kind of in the middle of the range, or no, I think these are the natural white. There are three different, there's a cold, there's a warm, and then there's like a natural kind of in-between color light. And so these are the RGBWs though, which just means that there are actually 4 values that you send to these: red, green, blue, and white, because there are 4 little LEDs inside of each of these. There's like an explicit white pixel that gives you a really nice, beautiful white light for these. So I'll show you how you can actually support these in MicroPython. It's pretty simple to do this. But this is what I wanted to do. I wanted to just play around with programming some neat kind of colors and animations on this, because like I said, you know, I can clip this battery, it velcros onto the back here, and then this whole thing is kind of a self-contained thing that you can put onto, you know, clothes or something like that, or just a neat little thing. I mean, you could even maybe like chain these together, have multiple of these displays or something if you wanted to get really fancy with this. So that's what we're gonna play with here. So let me just plug this thing in real fast, and then we'll get started here. Oops, let me get the right direction. There we go. So we've got that plugged in, and it's not running anything right now, but we'll come back to this. Okay, so in this stream, I wanted to play around with something that some people might be familiar with, some people might not be familiar with. So I wanted to implement an old school demo effect called plasma, and I'll show an example of it, and I'll actually show you a little bit more about it. So this is a demo, and a demo is a computer program that demonstrates interesting graphical or music or sound effects. Think of it like computer artwork that's generated in real time. So you're kind of showing off your programming skill. You know, if you can make like a 3D world that you're flying through, you're demonstrating your programming talent in some ways. There's a long history to the demo scene. It goes all the way back to the 80s with the early home computers and just people trying to show, hey, look at this cool thing that I did. And, you know, maybe that was neat programming, neat music, neat graphics, things like that. And it's still going on today. There's a really rich and vibrant demo scene. But I'll show you some cool stuff. This is from a demo from 1993, one of my favorite demos actually, Second Reality by this group called Future Crew, which were kind of at the height of the demo scene back in the early days. So remember, 1993, the best PC that you might have, and you know, you were lucky to have one of these, would be like a 486, or maybe even not even a 486, a 386 for sure. But you know, this was the early days of PCs, and so this is a little excerpt from it, and I don't think you'll hear any sound from this, or you might pick it up from my computer. I don't know, we'll see what happens. The sound's not important. The interesting thing, so if I hit play here, now notice this is a cube and it's rotating around, and that's not the actual effect that I'm gonna do. But look at the colors on the cube, these kind of like waves of bright colors that are moving around and, you know, kind of hypnotizing, really cool effect. Again, remember, in 1993, this ran on like a 386 or a 486 at full speed. Like, this was mind-blowing, because if you remember back then, like Doom and some of the early 3D games were just being created. Like Wolfenstein 3D might have been the height of 3D graphics that you'd seen. Now this is a different effect, but we'll kind of go back just to show that plasma effect again. So this is a really cool kind of color effect. It's called plasma because I think it's kind of meant to look like what, I don't know, what people think plasma might look like. I mean, plasma is, I guess, a fourth state of matter, but I think it only happens at such high temperatures and things that you don't really have a chance to see it yourself. But it's this cool kind of neat organic oozing effect. And you might look at it and think like, wow, this is like really complex animations and like something's going on here. They're really doing crazy stuff. But I'll actually show you a little bit more. So way back in like probably 1997 or so is when I first saw this website. But this website was actually created in 1994, and the amazing thing is this website has not changed since 1994, which I think is great. So this is like a time capsule to what the web used to look like. Although, to be a little pedantic, the background image here, this little circuit board thing, back in 94, 95, we didn't have background images on the web. They were all just gray backgrounds. At some point, I remember Netscape 2.0 was released, and that added, I think, background images. And so, every website had background images. The other funny thing here is that this broken counter link, if you remember back to the 90s, every website had a hit counter. So you'd go to the website, and every time you viewed the website, there'd be a little number here that would increase with every person that visited the website. So you could watch like, oh, whoa, 1,000 people visited in an hour. This is a popular website. Anyways, though, we could talk for hours about the old web. But this is cool. This is literally a time capsule that has not changed at all. But this was a really cool site. This was made by a guy who went by the handle Trickster, really big in the demo scene. He had this hornet.org, I believe, is like this archive of all this demo scene stuff. So really cool stuff that you'll hear about. I think Jim Leonard is his name. And he's actually just recently, a couple years ago, did a demo, a modern demo for the old IBM PC, the original PC, I want to say. I can't remember the exact model number, but there's still new stuff coming out for old hardware, which is just amazing. Anyways, this website is really cool because back in the early 90s, you would download something like Second Reality. And by the way, we didn't have YouTube. You would get this from a BBS. You wouldn't probably even get this from the internet. You would dial up to someone's computer in the local area, like in your neighborhood or maybe in your city, and you would go to some file board and you'd see this thing that's like Second Reality. Although you wouldn't even see Second Reality. It'd be like 2ND-REALTY or something, because you only had 8 characters in DOS back then. Because remember, you weren't even using Windows back then. But anyway, so you download this thing, you'd run it, it would blow your mind, and then of course, if you were into computers, you'd think, how do I make this thing? Like, I want to make a demo like this. This is amazing. And so you would find, maybe you one day would get access to the web, potentially through like your school library, or maybe your friend somehow had a connection to an ISP, because all the ISPs were local. They were basically bulletin boards that started to connect to the internet. But anyways, I could go on and on about the early internet days. So you'd find this website one day that tells you PC demos explained. Okay, cool. Let's see how all these effects work. And this is a cool site. Again, I'll try to put links in the description when this goes up on YouTube, so you can just go look at this. But this went through and showed off like all these different effects and things that you can see. Like, okay, and this is really funny too. Like, this was the full-size image back in the day. Back in 1994, this image would have filled your computer screen because your resolution was probably like 1024 by 768, and now I'm on a 5K iMac, which is just insane, 20 years later, progress. So now this looks like a postage stamp. But this was pretty amazing. This is like fully shaded 3D graphics. These are like some fish that are swimming around, some kind of cool torus, or like you're inside of some 3D thing with like some, not really texturing. It looks like they've just colored some of the polygons inside of here to give you some neat effects here. But that's what you had to do back in the day, because 486 couldn't do like real-time shading and lighting, or if it could do that, it was in very constrained kind of situations like these demos. But this was neat, and this goes through and just looks at different effects. And if I remember correctly, it even tells you like how to do some of these effects, or like where to get started, what Usenet groups. Usenet was like, gosh, I don't even know a modern equivalent of Usenet. It's like a message board, but it was you had to use client applications. It's still out there, I think, but I don't know if anyone really uses it as much anymore. But of course, that was where you learned to program demos. So this is a cool site. You can also look up on Wikipedia. They have info about the plasma effect here. And so that's what I wanted to focus on and see if I could program some kind of plasma-like effect on the NeoPixel grid here. Now, I only have 40 pixels. It's 8 pixels by 5 pixels in this grid, so I'm not going to get as nice of an effect as like one of these, but we'll see how this works. Now, the Wikipedia page talks about the way this works. It's really just an implicit surface that you're generating in computer graphics. So like, I'm just going through each pixel, and for each pixel, I'll look at its X and Y position. Like this pixel is maybe 4 pixels over on the X and maybe 3 pixels down on the Y axis here. So based on that position, you just run it through a function. Like right here, it's showing, okay, if you take the sinusoid of some noise function times some frequency, and then use that to figure out what color that pixel should be. And you do that for every pixel on the screen. And then if you just choose interesting functions here like sinusoids, cosines, and you add different scaling factors to it, then that's just going to change how these different things add together, and you get these cool effects like this. And so it just kind of adds together to add different layers of complexity to this. So you just start with basic math functions like sine and cosine. And remember, sine and cosine are useful functions because they're basically like infinite functions, and that you can just throw a stream of numbers at them and they'll give you a wave, like a sine wave goes up and down forever. And so that way, if you've got like time, and so time could be kind of what you use to do your animation. And if you throw time into there, so as time increases, you just get that kind of slowly moving, or it could be fast moving depending on how you scale that value. You get some regular signal. And then if you add things together, so like add a sine and a cosine, and maybe use one for your x direction and one for your y direction, then you'll get interesting effects like that. So this Wikipedia page is kind of useful, but this page was actually more interesting to me. This kind of building plasma online with JavaScript page. I'll put a link when this goes up on YouTube so you can see. But this is cool because this kind of breaks down step by step. Okay, let's start with just taking a sinusoid based on your x position and add the current time. And so you can see that just animates like a bar that's kind of moving left and right. But notice it's a nice kind of ramps up and ramps down, because that's the way the sine function works. It goes from -1 to 1 with a really nice smooth ramp. And so you're just kind of using that to change the intensity. And then you can get fancier and say, okay, well, we're changing the x-axis. Now let's change the y-axis too. And so now you get like maybe a diagonal kind of thing because you're changing both axes. And maybe let's like spin them around, so change like the angle based on the current time. And so then you get these cool kind of spinning effects. And then you get even more advanced and like start adding things together. And so you get kind of these circular effects. And then if you combine like all three of these together, you get these really interesting kind of organic combinations where it ultimately is a function that's going to repeat after some amount of time. But when you look at it, it just looks like some cool random, but organic in the sense that you don't see like a hard edge or, a part where it ends and where it starts. It all kind of smoothly blends together and moves around like this. So that's really the whole basis. And then you can see up here they've colored some of the components. And so it talks a little bit about how, once you have this basic intensity, you can run your color components, your red, green, blue colors, through sine and cosine functions again. And so then you get cool kind of organically changing color patterns here. And then this page specifically goes through and implements it using OpenGL shading language, which is how you would want to do this nowadays with modern graphics, which is kind of cool because like this runs entirely on the GPU. Like that Future Crew thing, this was all running on your processor. So like, your 486 was actually computing each of these pixels. Whereas nowadays you have a whole graphics card where you don't want to do any of this processing on the CPU. It's actually way too slow to do some of this stuff. But in our case, we're just going to see if we can do some of this stuff on this grid of pixels with MicroPython here. And so that's the cool thing. If I'm going to do this in MicroPython, so the code should be pretty straightforward as far as, I've got all the math functions that I need, like sine and cosine and stuff like that. There's a NeoPixel library that we'll use. So let's just kind of jump in here and just start hacking on some of the code. And like I said, this is a little bit unscripted. I did play around a little bit ahead of time and have kind of an example demo that I can fall back to. But I figured let's just start from scratch and just see, what it takes to create something. This is actually the code that I was creating ahead of time. But let's make a new file here. And before I get too far into this, I will show, because I'm using the RGBW NeoPixels, right now in MicroPython ESP8266, there is a NeoPixel driver. It's only for the RGB NeoPixels, so not the Ws, but it's really easy to add the Ws, and eventually we're going to publish a library for this. But basically, I took the NeoPixel library from MicroPython ESP8266, and I literally just added a fourth component here, the W component. And so now whenever you write out pixel data, you just have to write out the red, green, blue, and W for this, whereas the current NeoPixel library only writes out the red, green, and blue, which makes sense because it only supports that. So real easy to extend it. So basically I made this little RGBW NeoPixel class, and then I froze it into my MicroPython firmware. So I have a custom MicroPython firmware build on here with my NeoPixel RGBW frozen into it, just saves memory, you know, because I'm not going to change this code much. It's kind of the basic code. My script, I don't necessarily have to freeze into there. Okay, so just to get started with this, maybe I'll go to, well, let's just start on our machine here. And so let's make a new file here, and I'll call this maybe the stream plasma, because this is the version that I'm doing live on the stream here. And just to start with, let's initialize our NeoPixels and like turn on pixel 1, just so you can see where it's at. And then maybe we'll move that pixel around and animate it and build on top of that and go from there. So to do the NeoPixels, you have to import the machine module and then the NeoPixel W module, which is the special one that I created. But if you don't have the the RGBW pixels, you just want the NeoPixel module. But I'm going to do the W one, and then I'm going to need to create a NeoPixel object. So this is just going to use that NeoPixel W class, and then there's a NeoPixel RGBW class, or sorry, NeoPixel W module. There's a NeoPixel RGBW class inside of there. This needs to know which pin the NeoPixel is connected to, so that's pin 15 on my hardware, and then the number of NeoPixels, which is 40 NeoPixels for this. And then what I want to do, I'm just going to clear all the pixels so I can use the fill command, which will set the color of each pixel. This takes a tuple of 4 values. That's the red, green, blue, white value. So if I just set 0, 0, 0, 0, that's basically completely off, which it is right now, so we won't really see anything different. And then if I use the write function, oops, neopixel.write, then this will just send out the color data. So the fill won't actually change the pixels, it just changes the buffer in memory, and then write actually goes out and pushes the data out to the pixels. So we'll do that, and then let's just turn on pixel 0. So the very first pixel, we'll set this one to a red color. So we'll do that. And then how about pixel 2, we'll set to a green color. And so the colors, basically, each one has a component that goes from 0 to 255, and a value of 0 means like totally dark, 255 means completely max bright, and then, you know, any combination of these 4 pixels will just change which color you see. And you can have, like, if I want, you know, a halfway green pixel, then just 128, so, you know, half of the value of 255 in this case. Okay, so I just want to demonstrate all the pixels. So we'll say the third pixel should be maximum blue, and then the fourth pixel, let's say, is maximum white, so 255 for that. Okay, and then I need to call the write function again to just send these out to the pixels. Now to run this script, I'm going to use the ampy tool. I've done a whole tutorial and video on this one. Neat little tool that I made that lets you send MicroPython code over to your board to run it. So I'm just going to run, and I've already, I created this environment variable. If I show you the ampy port variable, it's basically set to my Scilab's USB to UART. This is the serial port for my ESP8266. So because I've set this environment variable, ampy will pick that up and it knows which board to talk to. So it's going to send the code over to this board. I don't have to specify this as a command line parameter every time that I run this. So there's a run command in ampy where I can just point it at a script like my streamplasma.py, and I run that, and okay, cool. So it just turned on a bunch of pixels here. So you can see, okay, pixel 1, or whoops, oh boy, oh, I just scrolled up here on accident. There we go. So pixel 0, or you know, the very first pixel is right here, and it's red. And then right next to it is pixel 1, pixel 2, pixel 3, and you can see that's just green, blue, and then white. And then if I want, I can kind of knock these color intensities down. So you can see like that white pixel, it's pretty bright, at least on the camera, because it's trying to, you know, do some exposure adjustments here. So maybe if I run this again, then the white is a little less intense. You can't really tell here. Okay, cool. So I mean, that's the basics of using the NeoPixels. Now let's do some quick little animation here. So let's have it just move, like we'll take, you know, the first pixel, we'll set it red, and then like a half second later we'll move it over, and we'll move it over, and we'll just kind of move through all the pixels just so you can see and kind of intuitively understand, you know, this is like position 0, 0, and this will be pixel 40 at the end here, or pixel 39 rather, at least the index for this. So okay, let's do that. So we just want to do a loop. We'll keep this at the top where we clear all the pixels and turn them off. It's probably good to start with that. And then I'm going to loop forever inside of here. So I'm just going to do a while true loop. And then in this loop, I want to loop through all of the pixels. So for I in the range of 40 pixels. And then let's go and let's set the pixel, well, first let's clear all the pixels, because think, every time this loop runs, I'm going to clear all the pixels. And actually, it's not even here that I want to put this. I want to put this at the start of every time I, think of it as like 40 different frames of animation. And so for each frame, I'm going to move over which pixel I turn on. And so at the start, I want to clear all the pixels. So I just turn everything off. And so we'll do that. So we'll say clear all the pixels with this command. And then I want to set, okay, the current pixel. And so I'm going to loop through all 40 pixels. This I in range of 40 will go from 0 to 39. And so we'll just set this to 255, 0, 0, 0. How about that? So this will be red pixel. And then let's just delay for a small period of time. So we'll import the time module, and there's a delay function in here, time.sleep. And we'll say sleep for like a quarter second. So we'll make this kind of fast. Okay, so let's save this. Now I'm going to run this a different way. I'm going to use the -n option, and this means no output. It tells Ampy to run your script, but not wait for any output, because when I ran it before like this, it actually waited for my script to finish running, and it collected any output, which I didn't have, and it printed it out to the screen. The problem though is if I try that with this script, I have an infinite loop here, so it's never going to return. It's just while true. It's just always going to go through this animation of moving this pixel across. And so in that case, I want to tell Ampy like, hey, this script is just going to run forever. Don't wait around and try and get any output. And so that's what the -n option does. If you have a script that takes a long time or has an infinite or like a main loop like this, you probably want to use the -n option. So, okay, so I'll run that and we get nothing. Uh-oh, so I must have a mistake here. Let's see, what I'll do is I'll remove the oh, I know, I forgot to use the write function. So let's do that next. So np.write. So let's put that in there. So that was kind of a classic mistake with NeoPixels. You think like, oh, I'm just going to change the color. Well, that doesn't actually change the color of the hardware. You have to call that np.write function to write out your buffer to the actual hardware, because there's a certain signal that has to be generated with a specific timing and all kinds of details and stuff that are hidden. So, okay, let's try this again. There we go. Okay, so now we see this thing's kind of moving. And so just going through each pixel, 0 through 39. So pixel 0 is up here, pixel 39 is going to be down at the bottom here, or I guess at the top here for this. And it just goes forever now. So it's just going to loop forever and go through and show all these pixels. So, okay, that's kind of cool. Like, basic kind of animation effect here. We're just moving things around. And if I wanted to speed it up or slow it down, like if I wanted to really speed it up, I could say let's only delay for like 1/10 of a second in between each iteration. And so now you see it moves a little bit faster like this. So pretty cool, pretty simple and straightforward. Okay, let's start to get a little more advanced now. And let's just start playing with some of the functions that this web page shows here. So we'll say, it starts with, let's just look at the X direction and see if we can get some kind of a neat like bar of color that fades nicely and moves left to right like this. And so the two things that I need to know the X position and the Y position of each pixel. So basically I'm going to loop through each pixel and I know its X and Y position. And then I also need to know the current time. And getting the time is actually a little bit interesting in MicroPython. So I'll show you in the time module, and this is the MicroPython ESP8266 documentation. If you go to the MicroPython libraries documentation and then the Python standard libraries, these are the libraries that they've implemented. The micro-time module at the bottom here is basically like the time module in normal desktop Python. And what you can do, there's a function, so normally in Python, and actually here, let's just connect to the web REPL, or the REPL, serial REPL on this board first, just so we can run some Python commands, and I'll show you what the time function does. So I'm going to connect to the serial port, and I'll press Control-C just to stop the script that was running. Okay, so if I import the time module, and normally in Python, if you want to get the current time, you call time.time. And on MicroPython, you get a value. This value is in seconds, so you don't actually know like the number of milliseconds. On desktop Python, and actually I'll show you on my Macintosh here, if I run Python, and if I import time, and if I call time.time, I actually get a floating point value here, which is kind of cool. Like you get the number of seconds since the Unix epoch. I believe that's the time that it gives you here. And you get sometimes down to like the millisecond accuracy. So this has like 3 decimal points of accuracy. So this is pretty nice. So actually more than 3 decimal points in this case. You know, you can get some decent accurate timing with this. So if you're doing like an animation loop, and your loop runs really quickly, like it might only take like, you know, a couple milliseconds for your loop to run, you really need to know like a couple decimal points of time accuracy for that. And so in Python, the time.time function is sometimes good enough for it. Now in MicroPython, it's a little bit different because, you know, your hardware like your ESP8266, it doesn't really have a clock built into it. Like the CPU runs at a certain frequency, and based on that frequency, you can kind of infer after a number of clock cycles, you know, a second of time on the wall clock has probably elapsed. But there's no dedicated hardware in here. There's no like internet connection like on your PC. Your PC probably connected to some server on the internet when it booted up and it found it had internet access. And it got the current actual time, you know, set by some atomic clock, and it's able to keep really accurate time. You don't have that luxury on little hardware like this. So it is interesting in MicroPython that you do have this counter that increments based on the number of seconds, but I want to get a little bit more accuracy. And that's where, if you look at the documentation here, there are some functions that are useful. There's a ticks ms, and this gives you a millisecond tick counter. And there's a ticks microsecond, or ticks micro s, or us, that gives you a counter that's based on the number of microseconds. Now these things aren't perfect. They're not giving you the actual time, so they're not telling you. And even time.time isn't telling you like, you know, it is September 23rd at 6:31 p.m. PST right now. You're not going to get that level of accuracy. You might if you add a real-time clock module and you set it and you have a backup battery attached to it and all that stuff. But usually you're not going to have that. But, you know, I don't care about the exact time. I just want to know like how many milliseconds have elapsed since the last time my loop ran. And this ticks ms function should be good enough for that. Now it does warn you that this value is going to wrap at some point. So it's, you know, this value is always increasing based on the number of milliseconds. And here, like, let's just call it. So if I call time.ticks_ms, you know, you can see this. And then roughly a second later or so, it increases by about 1,000. So, you know, if I call this roughly once a second, you see it goes up by a value of about 1,000, which is there are 1,000 milliseconds in a second. So this is useful though, because, you know, I don't really care about what the exact value is. I just care between the 2 times I called this, you know, I could subtract the difference. So we'll say like old equals time.ticks ms. And then we'll say, you know, delta equals time.ticks ms minus old. And so that, and now if I print out delta, okay, that was like about 7 seconds elapsed. And if I really wanted to see, I could divide it by 1,000. And so it was 7.08 seconds that elapsed between running these 2 commands here. So that's one thing you can do. Now they are careful to tell you these values can wrap around. So at some point, this value is going to get so large, MicroPython can't keep it inside of an integer value, or I think like a long integer. I can't remember what the exact value is, but it's actually going to go back to 0. And so you might get into some weird situation where like your old value is bigger than your new value, like when you call it, because if it wraps around, it goes back down to 0. You get into this weird edge case. They do have a ticksdiff function that you can use for that. So you can do time.ticksdiff, and I can say time.ticksms, the current time, and then maybe my old time, and this will tell you, or I think, let's see, what's the syntax for this? The syntax is, oh, I want the old one first, so I gave it in reverse order. So if I give my old one first, and then my new one, so we'll say time.ticksms, then this, okay, this is kind of telling you, here's, you know, 74 seconds. And this function apparently can handle when it wraps around. So if you're looking at a delta in the ticks, you probably want to use this diff function, but I honestly don't even really care because I just want some value that increases every millisecond. And so then that's going to let me use that as kind of my current time. And I don't care the exact absolute value. I just want to know that it's going to increase by 1 every millisecond. So, okay, so I think that's good enough. I think we have the components to start doing some of these animations. Like I know my current time in milliseconds, and then I know the X and Y position of each pixel. So let's start to implement some of this stuff then. So let's see, we're going to do an infinite loop again. And maybe at the start of our loop, we're going to clear all the pixels, just turn everything off, because every frame of animation I want to start with a blank slate. So we'll clear all the pixels to a 0 color value with that fill command. And then let's go through, and I want to loop through each X and Y pixel position. So for X in range of, the number of pixels I have in my X dimension are 8. And so that's what I'll use here. And then we'll do a nested loop for Y in the range of 5, because I have 5 pixels going from top to bottom here, basically, for that. And just to make this program a little bit nicer, let's put these as constants at the top. So we'll say like pixel width equals 8, pixel height equals 5. And then the cool thing is, I know the total number of pixels is going to be my pixel width times my pixel height. So this just makes it nice. If I went to like a bigger or a smaller grid, I can just change these values. And then down here, let's put in pixel width instead of the hard-coded value. So we'll say pixel height for this. Okay, so these two loops then are going to loop through each of the pixels, each position here of the pixels. Okay, so now then the next thing they do is basically for each pixel, you compute this v value as the sine of your x position times 10 plus your current time. And so to get my current time, let's do that next. And so let's say my time, and actually I don't want to use time because I've imported time, and so that's a module that's in kind of scope, so I can't make a variable that's called that. But we can just say current equals time.ticks milliseconds, and I'm just going to divide it by 1,000. So now my time is in seconds, but it's floating point, so it's going to be like 500, kind of like you saw right here, like I might get like 580, 5,808 .031 or something like that. So this just tells me that my time is in seconds, which is how this code expects it to work. Like you have some time value that's going to be based on the number of seconds, but it doesn't have to be like that. I mean, I could use milliseconds and things like that if I wanted. Okay, so now let's actually compute this intensity value. So I want to import the math module in MicroPython. And so math module is really nice. And again, if you go back to the MicroPython documentation, there's the micro math module, or I don't even think they call it micromath, it's just called math. I just went to the wrong page. There we go. So you can see this has pretty much every math function you could want inside of here. So sine, cosine, square root, all the important stuff in here. So we're going to use this a lot for our code. Okay, so let's just take then, so we'll say we'll create that v, our intensity equals math.sine, because it's in the math module, and then x times 10 plus time. So my current x position times 10, and I'm going to use 0.0 just to be explicit about floating point multiplication, even though in Python I believe it can infer that it should use floating point. I like to be explicit and just say, like, do floating point here. Even though you don't really technically need it right now, it's only once I add my current time to it that now it becomes a floating point value. But anyways, so this is exactly what they have in the web page here, though. So it's my current x position times 10, which is just scaling it, so just making it like a larger value, plus the current time, which for me I've called from this current variable here. So okay, so let's do that. And then the next thing that we want to do, I want to use this to set the intensity of each pixel, or of this pixel. So the next thing I need to know is, based on my x and y position, which pixel do I light up? Because in this NeoPixel object, it's just an array of 40 pixels. And so you actually have to do a little bit of math to figure this out. So you can do it based on, if you know the width of your pixel, of your grid of pixels, then you can know, okay, if my y position, if I should be at row, how about 3, like right here, then I know from the start down here at pixel 0, I'm going to be, one full row, a second full row, and then, nothing else. I'll be kind of, 2 full rows starting inside of that flat array of pixels. And so each row I know is pixel width wide. So, 8 pixels, another 8 pixels for the second row, so that's 16 pixels total. So at pixel position 17 right here, or actually 16, index 16, that's going to be that y position of 2, or the third row actually in here. So that's kind of what you want to do to do that mapping from like a 2D grid into a one-dimensional list of pixels. This is super common in graphic stuff. You know, if you've got a 2D buffer, but it's usually saved as like a single array. And so you have to map between the 2D position and your kind of one-dimensional array. So we'll just do that. We take our Y position times pixel width, and then we add our current X position to that. And so again, that's just going to offset, you know, based on which row you're at, that'll offset you some number of width number of pixels up to that row. And then this little plus X just says, once you know which row you're on, just move X pixels into that row. So, you know, if you're at X position 0, you're going to be on this right-hand column. If you're X position 7, you're going to be all the way at the end on this column over here. So that's just kind of how you do that mapping inside of here. And okay, so now if I know its position, I can set the intensity of the pixel. And I'm just going to set, let's set that white pixel. So we'll say red, green, blue are all 0. And then the white pixel we can set to this value. Now I want to be careful because my pixels are set, remember the component values go from 0 to 255, whereas the sine function will give you a value that goes from -1 to +1. So remember, it gives you that nice kind of looping, or not really looping, but nice smooth signal that goes up and down. So it goes from -1 all the way down to, or all the way up to +1, which I don't really want. I want to go from 0 to 255 and back down. And so what I can do a few things here. So I can move my sine function up so that instead of going from -1 to 1, it goes from 0 to 2. And so if I just add basically 1.0 to that, so now if I have a value of -1 from my sine function, I'm going to add 1 to it, so now that's 0. So, and the way the sine function works, you'll never get a value below -1. And so that just means that I know my minimum value now is 0 when it gets offset by 1, and then my maximum value is 2. And so I've got a value that goes from 0 to 2, but I actually want a value that goes from 0 to 1. Because if I have a value that goes from 0 to 1, I can multiply that by 255, for example, and that will scale, you know, then I'll get some value that's like 128 when it's exactly in the middle, or 255 when it's at 1.0 and it's exactly at the top. And so the way to do that, I just take this and I divide it by 2. So if I divide this by 2, then I'm basically saying, okay, you know, I took my sine function that goes from -1 to 1, and I offset it by 1, so now it goes from 0 to 2, and then I divided that by 2, so now it goes from 0 to 1. And then with that, I can say, okay, now I have my v value is within the range of 0 to 1, and if I just take that and multiply it by 255, then that's going to give me a value that goes from 0 to 255 based on your minimum to maximum intensity value for that pixel. And I do want to just make sure that this gets converted into an integer. So we'll say 255 times my v value, and then be explicit because it actually won't work with floating point values. It needs to have an integer value in here. So I just convert this to an integer value. It's going to take the floor. So if it gets a value of like 238.7, it's going to take 238, which is good enough. That's, you know, going to be close enough here. So okay, so this is pretty cool. Let's try this out. And oh, hey, I always forget this. So after I write all my pixels, I should do my neopixel.write function call. So, or you know, I set all my pixel data inside of here, and then I'm going to call my write function here. And actually, I'm just thinking now too, I don't necessarily need to take my current time every time I'm looking at a pixel inside of here. Basically, what I'm thinking I'll do is, let's take the time at the start before I get into my loop, so that, you know, because that time isn't really going to change that much in between each pixel. It's really in between each of the loop iterations that I care about changing that time. So we'll pull this up and put it up here. And so now, just for each of the pixels, I just compute the intensity based on this equation for the time, and then you know, doing this little bit of magic here to push it into the range of 0 to 1.0 rather than -1 to 1.0, and then using that to set the white pixel intensity value for this. So okay, so let's save this and let's see if this runs, because hopefully I haven't made a syntax error on this. And so we'll say this, and okay, so hey, something's happening here. And so you can see it's pretty bright. My camera just had to like dial down the exposure quite a bit. So let's actually change that. It's actually so bright, like when I look at it, it's kind of like, whoa, I'm seeing stars in my eyes because these pixels are bright. So I was thinking, let's just do a max brightness. And this is just a value. Let's take this 255.0 value and just make it something that I can change with a simple variable. So we'll say max bright. So now if I knock this down to like 100, this is going to change the intensity of the light. And so if I'm going to run this again, and not much really appears to have changed just because the camera is auto exposure changing things, but it's a little less bright when I look at it. I'm not as blinded now, so that's good. So this is handy in that if I want to make this max bright, I can just change this variable. But I don't. If I want to develop on this and not blind myself, I can crank it down a bit. Now the thing you might notice is that it's not moving as kind of smoothly as this. Like you can see it's moving. Like there's this row that kind of turns on and off and moves around. And the one thing is that this scale factor is a little bit different because remember, I only have 8 rows of pixels here, whereas in this animation they have, I don't know, at least like 50 or 60 rows of pixels here. So this is something where this is kind of the fun of it. You can just start experimenting and changing these values. Like if I increase this to 50, so like x times 50 plus the current time, let's save that and see how this changes things. So I'm going to run it. And now you can see this is kind of cool. Like we get, it's like a wider, these, the bands, I guess. This is kind of like changing the width of the band of color. And so you can see it's a lot wider as it moves across. And then let's see what happens if I scale it down. So like let's just get rid of it completely. So it's just my current X position plus the current time. And so we'll save that. And now let's run this and see how that changes things. So this is kind of cool. Like this is now you get these nice, smaller size bands like that. And there's nothing stopping me. If I wanted, I could make a smaller value. So times like 0.5. And so this is going to actually make the value smaller. And so I should probably see that, now my color bands are, oh, interesting. My color bands are a little bit larger in this case, but you get kind of interesting variations here of how things change. And I know I'm morbidly curious. So what if I change this to a really small value, x times 0.05? Let's see what happens here. Because this is kind of what you want to do. You just want to experiment with things and see. So, okay, that was kind of cool. So it's like, you get these really wide bands and then like a wider kind of, you can see the band where it's turned off like that. So kind of seems like the band width is inversely proportional to the scaling factor that I'm using here. And I bet if you sat down and thought about the math, you could actually understand a little more about like why it's doing this. Maybe a good exercise for the reader. But let's just try, well, how about 2.0? What does this look like if I just double it? Does that give me some interesting value for this? So that's kind of cool looking. So you get kind of this neat effect like that. I actually, when I did this ahead of time, I liked just keeping it with no scaling factor here and just using kind of the current value like that. So, I think that gives it's pretty obvious. Like there's some bands that are moving across like that. So, okay, so that's cool. And again, all that's happening here is I'm just looping through every single pixel, like each X and Y pixel. I go pixel by pixel, and based on its X location and the current time in seconds, I'm throwing that through the math, the sine function, and that's going to give me a value that goes from -1 to 1. And again, remember the sine function kind of gives you this nice repeating waveform that just goes up and down continually. And then I just have to push that into a range that's easier to work with my pixels rather than -1 to 1. I want to go from 0 to 1. And then I just scale my pixel brightness based on that 0 to 1 value for this. So, okay, so that's cool. Let's keep going with it. And let's try this next thing. This is looking pretty wild down here. So now they're getting pretty crazy. So they're basically saying, okay, let's take the sine, but instead of just your X, let's take your X where now we're using the time as the angle inside of there. And then let's also add the Y position with the cosine of the angle. So cosine is like the inverse of sine. So you get a repeating up and down signal, but it's just flipped over. Like when your sine is up, your cosine is going to be down basically. And then they all just kind of match each other. So when you combine those things together, you get kind of cool effects like this. So let's just try exactly, what they have in here. So this is the cool thing, because with MicroPython, like, my Python code is going to be really similar to this equation. I just have to kind of convert to call the right math function where I need to. So, okay, so let's, I'm going to comment out this first one, and let's make a new v equals. So we'll say math.sine, and they have 10 times math.sine of your current time divided by 2, and then plus your y. Oh, sorry, I missed an x times. Oh no, sorry. So this was 10 times x times math.sine plus y times math.cosine, and then of my current time divided by 3. Oh no, I'm off the screen now here, so let me just move this over a little bit. And then let's see, so I'm up to here, and then I want to add my time after I have this value that's times 10 here. So let me just make sure I get all the parentheses correct here. So yeah, so now I want to add my current time to this. Okay, so again, so I'm basically taking, let's look at the inside value here. So I've got my math.sine of the current time divided by 2. So this is basically, as my time changes, this angle is going to change, and I'm going to multiply my x position by that. And then adding to this value, I'm going to take the cosine of the current time scaled by a different value, so it's just going to rotate at a different rate, times my current y position, add those two together, and then multiply them by 10, just scale them by some value, then add the current time to it so that I get some value that changes over time, and then throw that into the sine function here, which is going to give me a value that ranges from -1 to +1 again. And again, I want to do that scaling so that I get it into a range of 0 to 1. So I'll just keep this same code here. And that's it. So let's save this and see what it looks like. And I remember when I was doing this earlier, I tweaked some of these constants a little bit, and that's the fun of it. Let's just see what happens when we change some of these constants. So we'll run this code, and now we see it's like, whoa, there's some funky stuff here, but you can kind of see there's like bands that are rotating around a little bit. You can see like lines that are kind of like spinning, some angles here. And if I look at what they show here, yeah, I can kind of see these like spinning and like zooming in and zooming out kind of angles of things. We're getting the same effect on our pixels here, which is really cool. So let's go back and let's play with some of these constants. So like this 10, let's bump this guy up to 50. Let's see what happens. I didn't even try this, so let's see what's going on with this. So okay, interesting. This thing's looks like it's moving a little faster. It's, maybe this might be kind of controlling like how much it zooms in and out or something like that. That's kind of interesting. Let's set it down to like a smaller value. Let's just put 1.0, so it's not really doing anything now. Let's see what that looks like in this case. Yeah, that's what I was using earlier. I like this one. This kind of slows it down a little bit. So now you can really see that there's like these diagonal lines that are kind of rotating and zooming in and zooming out, and this is already kind of a cool effect. And I don't have to do just the white color with this. If I wanted, I could make, how about the blue color for this? So let's save that. And now when I run it, now I get some cool kind of like blue, colors like that. That's kind of a cool effect like that. Neat, like blue diagonals that just kind of smoothly, organically move around like that. That's pretty cool. So I like that. Or how about this? Let's do full red. So now we'll get kind of pink and blue for this. Oops, I don't want to do 255.0. Okay, so now if I do this, so wow, look at that. So you get kind of red, and then where it's blue, you get like a pink color because your red and blue are combining for that. So that's kind of cool. I like that. And actually, maybe instead of 100, let's do, or instead of 255, let's do 100 so that, I want to match my max brightness level here. Because right now the red is kind of like super powerful and overwhelming. So I do that. There we go. Now it's a little nicer. So you get kind of red and blue. So that's kind of a cool demo effect right there, I think. It's like neat bands of color moving around, and it's pretty simple as far as the code goes. Like this function's a little cryptic, but that's kind of the fun of it. It really doesn't matter. Like, let's change this to 20. Let's change some of these components and see how it changes the animation here. So, okay, this looks like it's slowing down how fast it spins from the way I'm looking at this, which makes sense because if I'm dividing by a large value, that's going to decrease the value that gets passed into my sine function, and a smaller value it's going to change at a slower rate. If I divide this by a small value, which is actually going to be like multiplying it, this should speed it up. So if I divide it by 0.5, this should be faster if we see this. And yeah, this does kind of look like it's faster in one of the dimensions. So that's kind of cool. I like how that's a little bit faster like that. You know, it's like it's rotating in one way a little bit quicker. And how about this one? Let's make this 0.25. So now we should really have some quick spinning stuff with this. Oh, there we go. I like that. That's cool. That moves a lot faster than this. It's interesting. Like when I look at it myself with my eyes, I'm so close to it, it's a little bit hard to kind of see. But when you're further away, so I'm looking at it in the corner of the video preview here, and it looks a little bit nicer for this. Okay, I like that. Let's keep that effect. That's looking good to me so far. Again, this is more art than science at this point. It's just play with values and see how it works. But this is the cool, this is, you know, hey, who says that science can't be art? Because this is just the sine wave function. This is 7th grade math. Like there's nothing advanced about this. So it's just when you combine all these basic things, you get cool effects like this. Okay, let's go for broke. Let's see what else we can implement that they have here. So this next one's really funky. It's basically, this is somewhat of like the equation for a circle, if I remember correctly. And so we're just gonna combine all these components. Let's try it the way that they have it here. And so we're just gonna try and implement stuff exactly as they have it, and then we'll play with it more. Okay, so let's go with, I need to make a CX value first. And this is my X position plus 0.5 times the sine of my current time divided by 5. And then a CY component is my Y position, 0.5 times math.cosine of my current time divided by 3.0. And again, all these little factors, you can change yourself to adjust this. Now my V value is going to be math.sine of math.square root. And I'm going to take 100 times, and then they're basically taking they're multiplying CX by itself. So you're just doing the second power for it. So there's a math.pow function, and so I'm going to take CX to the second power, so squaring it basically, and then add math.pow CY to the second power. And now I've got a lot of parentheses to figure out here. So there's a parenthesis there. Okay, so this is my one component here. And then they add 1 because I think this keeps you from doing the square root of 0, which would give you a bad value here. And then, so let's add 1 to that. And now I believe we're done with the square root. Yeah, we're done with the square root. And then we just add time to it. So we add the current time. And then we're done with our sine function there. So, okay, so I've basically just taken their function and implemented it as is to set my intensity. And again, intensity math.sine going to give you that value from -1 to 1. So now we're just going to do that scaling magic to make a value from 0 to 1. And then let's, just to make this a little more visible, let's go back to doing this with just my white component again. So we'll save that, and then let's run this. And so now we see, okay, so we're seeing some interesting things. It's a little hard to kind of make it out. And again, I think that's because some of these scaling values are meant more for a larger pixel display. You know, I have less pixels here. So let's play with some of the scale factors. Like this 100, I'm going to knock this down to 1, like basically get rid of it. And let's just see how this changes things. And yeah, this, when I was playing with it earlier, this looks a little bit better. So you can see there's like, you know, this circular loop that's kind of moving this way. And, you know, this is kind of a circular loop. And it's, you know, like here's a small circular loop. And they're all kind of spinning around a little bit. And so that's, I think, pretty close to the approximation you see right here, where you get like these circular bands that are kind of like zooming in and out and moving around organically. So that's pretty cool. But let's play with some of these values a little more. So, you know, what if I set this to like 0.5? If I make a smaller value here, how does that change the animation? So that's, yeah, it looks like you get kind of like larger bands like we saw before. So that's kind of interesting. I liked it when it was just 1, so I'm just going to get rid of that value actually. And then let's change the speed of the time here. Let's go back to like 0.5, and how about 0.3? So this should speed up some of the way that it moves around. Let's see how this looks when I run this effect. So, oh, actually, maybe this slowed it. Oh no, I think this has kind of sped it up a little bit. So, yeah, this is kind of looking interesting to me. It's I don't know. I'm not sure if I like that or not. Let's try larger values. Let's try, like, if I divide this by 50 and maybe this one by 30 and see how this looks. So if I do this, so now I'm guessing I probably have slower rotating values inside of there, so it's a little hard to tell how that changed things. So I don't know, I think I kind of liked the 5 and 3 values that were there before. Let's try these. Let's see, what if I set 1.5 instead of 0.5 for these? How does this change stuff for this? So, ooh, I think I kind of like this one a little more. It looks like I see more movement with this. You know, it's like moving left and right faster. Yeah, this is looking a little nicer to me. It seems like I kind of sped up the X and Y movement with this. Let's try a larger value. Like, how about 3? And how about 5? You know, just try different values. Let's see how things work for this. There's no right or wrong way to really do this, you know, to be honest. Okay, so this is giving some interesting results. I wonder if, because I set different values for this, if it's like distorting it in some way. So let's set the same values for these and see how this looks for this. So this is kind of looking pretty cool. Oh yeah, you can see it. So it kind of moved around, like, you know, in a circle kind of pattern like that. I'm liking the look of this. This is looking pretty cool. So let's keep this effect or this value for now. So okay, so the next thing is then, what if you add all of these 3 things together? And that's actually what they're showing right here. So if I just take each of these V values that I computed, add them together, then you can start to get like these cool effects like this. So let's try that. You know, I've got my V values that I computed up here ahead of time with the different effects. So let's start with V equals 0. And then let's add to it my first function, which is kind of, you know, this moving left and right band. And then we're going to add this next function, which is like your rotating around band. And then we're going to add this function, which is that crazy circular thing here. So let's see how this works. Now, I do need to change things a little bit. So, you know, at this point, I've added together 3 of these sine functions. So, you know, my range of values could be a lot different here. So, you know, I could be from -3 all the way up to +3 in this case. So basically I want to offset these by 3 and then divide by 3 so that I know I get a value within the range of 0 to 1. Now this isn't exactly how I did it before, but I just want to try this and see how this looks. When I was trying this earlier, I did a different thing for this. So let's just see how this looks. If I run this now, and wow, okay. So things are a little different. Oh, I just lost one of the batteries on this light. Luckily, I have a spare battery, so it won't be too dramatic of a lighting effect here real fast. Let me swap this battery in. There we go for that. Okay, so this is interesting. It's you know, I don't see as low of a value. You know, I don't see pixels that are turned off as much as I did before, because I think the thing is, you know, when I'm adding all of these values together, there's less chance that I'm going to get, you know, just naturally, if you have 3 different values, you add them together, you're probably going to get mostly positive values from that. So that's why I don't think we see as dark of the pixels here. So the other way that I was kind of working with this, instead of doing this scaling, I could clamp the value. And I just want to go back and actually see if that's what I was doing in my function here. And, oh, actually, yeah, no, I still was doing some of that scaling in there, and then I clamped the value. So I don't know, let's play around. Let's see what works here. So let's keep this in. Let's keep my original +1 divided by 2.0 value here. Oh, and actually, no, sorry. This is wrong. I just realized this. So this should be +3 divided by 6, because when I add 3 to this, it's going to convert, you know, from a minimum of -3 at the very lowest value. If each of these sine functions is -1, I would get -3. That's going to push it up to 0. But then if each of these sine functions is 1, that's going to give me 3. Plus 3 is going to give me 6. Then I want to divide by 6 to get my my 0 to 1 value. So that's probably why I don't see the dark values here, because I'm not scaling by enough here. So now let's try rerunning this, and I should hopefully see a little bit darker stuff. Sort of. It's a little a little more obvious. I don't know, it's hard to tell. And again, because I have all these different things kind of added together, it's a little difficult to see, you know, exactly like what is the dark point and the light point. I don't know, let's keep rolling with this and we'll see how this goes. So let's add some color to it. Okay, so I've got my V value, and then the last thing they talk about on the page here is to add color, just set your red, green, blue colors based on your V component times some value. Like you could animate that value if you wanted. In this case, they're just using pi, so they're just basically using a sine wave to change your red, green, blue color component value. So let's try like this equation right here, where it looks like you get some really neat kind of colors and hues and things for this. So I want to compute my red, green, blue colors after I have my V intensity here. So okay, let's do my red color. So this is going to equal the sine of V times math.pi. Luckily, pi is already defined in the math module for you. My green component is math.sine V times math.pi plus 2 times math.pi divided by 3.0. So just scaling in some different ways here, the angle. And then the blue component equals math.sine V times math.pi plus 4 times math.pi divided by 3.0. And again, you can play with all these values. That's kind of the fun of it. Okay, so I have my red, green, blue components. Now I just want to do the same thing. So I take my maximum brightness value and I scale my red component for that. And then let's just get rid of this. So my white pixel I'm not going to use anymore. Although I guess what the heck. Let's compute a white pixel here. This is going to be really funky. I didn't try this before. So let's make a sine wave V times math.pi plus, how about 6.0? We'll just kind of follow the pattern that we're doing here, divided by 3. So you know what the heck, let's do an extra component here. Okay, and then let's do my max bright times my green component, and then my max bright times my blue component, and then max bright times the white component. Okay, so there's all that. Let's see what happens. I have not tried this, so this could be interesting. This could be a disaster. Let's see. Oh, that's kind of interesting. So there's definitely some color to it. I think the white pixel is like hiding a lot of the color because, you know, that intensity is pretty intense. Let's turn the white pixel off. Let's just set this one to 0 for this. Oops, let's go down to this. Because, you know, really plasma is all about the color. So, you know, adding white to it, maybe not interesting. Although, you know, there is no rule. You don't have to make plasma that's just that. Okay, there we go. Now it's a little more colorful in this case. And this is actually looking kind of cool. Like you can see, okay, now there's like interesting little bits of color and things that are there. You can see it's a little bit slower though. And some of this I think is a side effect of, you know, this is MicroPython, so this is interpreted code. There's a lot of math operations going on inside of here. You know, the math, like I'm calling the sine and cosine function at least 20 times it looks like inside of here. And so that's sometimes a slow function depending on how it's implemented. You know, math.power, math.square root, these aren't inexpensive functions. And again, this CPU only runs at 80 megahertz. Although the 486 and 386 that Second Reality ran on probably only ran at like 25 megahertz. So it's just funny that, you know, you could do these kind of effects. Granted, they had like VGA hardware that could do graphics effects, not accelerated, but, you know, it was a little bit faster at doing things. But this is kind of cool. This is starting to look like a plasma effect. You know, you can see like kind of organic blobs of color. Now there's a lot of tweaking, I think, to kind of be done here. So, you know, you really probably want to play with some of these values here, you know, adjust like these components, you know, that I had scaled before. Like, you know, what if I go back to 0.5 and 0.5 for some of these and see, you know, how does this change the animation and the color here. So like this kind of changes it a little bit. You know, you can see it's kind of moving around at a different rate there. So lots of things to play with. You know, I think the stream's kind of run for a little while now, so I think I'll wrap it up. But, you know, like I said, I wanted to just play with this old school demo effect. And then looking at a cool page like this that just shows you can just take the sine function, add it together, you know, use different variables like your x, your y position, the current time to manipulate the variables that go into that sine function. And you'll get these really cool organic shifting patterns and things without actually having to think about like, okay, you know, I want to make some smoothly organic moving thing. Like, you know, if you just saw this graphic and thought, well, how do I program that? That's kind of daunting. But when you break it down and just think about, you know, you've got sine wave functions and you're just moving them and using different components here and adding them together, then you can do cool things. This is really the mix of math and art. Like, you know, who says art can't be math? Like, this is a living example of it that you could pin to your shirt because it's written in MicroPython. You know, the code is pretty understandable here. You can go through and yeah, there's a lot of math in here, but you can read this and see that it's just, you know, going through each of the pixels and changing their color based on how we're computing these values for this. Okay, so that's it. So folks had questions, maybe throw them into the chat and I'll see if I can get to them here. So yeah, lots of people are saying math is cool. So yep, math is pretty cool. Let's see. Oh wow, yeah, lots of chat here. So I'll just go through real quick and see if there's any kind of recent question. And yeah, I don't see too many questions. So so I guess I'll wrap this up then. I will go back to the main view. Let's see, we'll turn this off. Well, and actually in the main view, we'll keep the hardware on. There we go. So hey, you can still see the demo effect here. So okay, so that's it. I'll wrap up this stream. This was coding an old school demo plasma effect. And demos were neat demonstrations of how good of a programmer you were, how good of an artist you were, how good of a musician you were. Started way back in the 80s. Lots of history still going on today. Lots of cool stuff. If I remember, I'll try to put a link in the description when this goes up on YouTube to some of the sites that have more info on demos today. I think Scene, I want to say scene.org is kind of the main, that used to be the main demoscene website. Oh, interesting. I guess it's changing. There's something else. This, I don't know how to pronounce this. I'm going to ruin it. I'm sorry for folks, but poet.net. This was another big one I remember. So check out some of these sites and like you can see like Revision 2016, this was like a party that just happened probably recently. Let's see, this was, a lot of these parties are like in Germany and in Europe. And so you can see, yeah, this was earlier in the year. This is a modern demo scene party. So there's people that are still making cool things. Now they've moved beyond some of these effects like plasma, but they've moved to really impressive levels these days. Like modern demos just blow you away. They're using the GPU and graphics acceleration now. Although some people still do the old school demos that, you know, you code this stuff by hand and really show how good you are of an artist. Oh, I realize I'm not showing my web browser here, but I'll put links to some of the sites I just mentioned when this goes up on YouTube. Anyways, though, so like I said, I wanted to play with doing some old school demo effects. This is the grid of NeoPixels that I was looking at. It's this thing. This is the NeoPixel shield for Arduino. But hey, it doesn't have to be for Arduino because I took it and just put an ESP8266 on the back right here. So there's an ESP8266, the Feather Huzzah version, little battery that powers it. And then all with MicroPython code, I've got some cool little animation effects. And, you know, I could wear this as like a neat little example of old school demo stuff. Eventually, I want to do like a scroller where you can have text that scrolls across, things like that. So real fun, cool stuff you can do with this. Again, all with MicroPython. So that's it. I'll wrap this up. This is Tony from Adafruit, so check out youtube.com/Adafruit. You can see this video and all kinds of other fun project videos. There was no guide or anything with this project. We're still doing a bunch of guides on just the basics of MicroPython and how to access hardware, but I want to start doing some more project-based things like this, you know, examples of cool animations. So I'll take the code for this and I'll put it up on a gist on GitHub so that you can at least go look at the code for this if you're curious to see. And then all the websites I mentioned, I'll put in the description on YouTube also. Check out twitch.tv/Adafruit. That's where I stream live. I like to do a stream every Monday, every Friday, at least twice a week, although I might kind of move around. Maybe the Monday stream might turn into like a Tuesday stream. Next week, though, I don't think I'll have any streams. just because I will be in New York for World Maker Fair at the end of week next week, so I'll be out at Adafruit headquarters. I'm sure you might see me on like Ask an Engineer or something like that, so we'll see what happens. So anyway, stay tuned and you'll see all kinds of more fun project videos. Lots of big focus on MicroPython. It's a big, fun, exciting thing. And like I mentioned at the start, I had a little, it's not out yet, don't ask, but this was the Feather M0 running MicroPython. So Scott, who's another person at Adafruit, has got an awesome port that's kind of in development. So you'll see more about that in the future. So until then, though, this is Tony from Adafruit. So thanks for watching. Bye.